Hello, and welcome to our next tutorial number 5. So this is another class in CFD for validation verification. So this is the subtract 2, and this is a very severe case in the sense that when after you develop your solution, so you have here your domain is a very easy domain, a 2 a straight pipe, or it can be 1D, 2D, 3D. We have here our initial conditions. And as soon as this system starts, you have a diaphragm here, and it breaks. You will have this shock wave system here, or this wave system. So first you will have an expansion fan, then a contact discontinuity, and a normal shock. And every single of these shock wave or wave are difficult to resolve. So we know across the normal shock wave we have a discontinuity, which is this one. Then we have the contact discontinuity, which is another severe one. Here we have that velocity and pressure are continuous. However, see that we have a jump at discontinuity and continuity in density. And then you have the expansion fan where all your properties will change very smoothly. So in general, this is tricky, difficult to solve, so we need to use robust, good numerics. And we have seen everything in the previous tutorials. Now let's put everything in practice here. And basically this is what we're going to have. We have an analytical solution, an exact solution, and then we have the numerical. So after choosing the right numerics, okay, in SV scheme, but also SV solution, we are going to get an agreement like this. Something else that I would like to point out, that also remember that we are going to work on a steady. Okay, this is a full unsteady problem. So remember that you have the piso eta and piso eta, which what is called in pimple. So remember that the piso eta iterative will let you do corrections here in the outer loop. Okay, the simple correction, and this correction will let you improve your solution. Very important when you are working with very severe problems. Okay, so let's go to the tutorial. I hope this will be a fast one. So go to the Chuck 2 folder, and here you will have 3 meshes: triangular, polyhedral, and orthogonal. So I will just address orthogonal, but you know, triangular, polyhedral, you will use the same concepts. And also you will need to fix the derivative for Laplacian schemes to take into account no orthogonality. But we have the orthogonal mesh, which is also a 2D mesh, 1D mesh, sorry. So let's work. In this case, it's very fast. And let's go to SV solutions, SV schemes. Let's explore this one. So look at that, SV schemes, and using default Euler, then grad schemes. I have here the full Gauss linear for every variable using Gauss linear. That might not be the best choice, but let's see what happens. And then for divergence, linear win. So remember that now also we have the energy equation. This is a compressible flow, so also you need to solve for energy. So depending on the formulation, you will have different terms, but I will use this formulation that I use internal energy. And every variable is discretized using this method, okay? And that's all, okay? It's a perfect mesh, limited 1. And in control did also, if we go here, see that we have the option to have a use all time state that I switch it off, or we can also use a delta t, fix the delta t. That probably many times is the best option. So we're using this delta t, and let's see what happens. Okay, so as you type as usual, run all, okay, load OpenFOAM. Okay, as you see, very fast case. By the way, also you will need to have Python 3 in this one to run the script. So as you look at the script, it will generate some figures automatically for you. Okay, so it will go here. This file is written in Python 3, so I will load also. I use Anaconda Python. Okay, I need to reload. And I will run again. This is a very fast case. And now it's doing the sampling. Okay, the plotting. And see here that it will generate these PNG files. And here you have your solution and the comparison. So see that we look at here. This is pressure, density, temperature, and velocity. As you see, okay, we might be close in some variables, but in other we're not very close. So how we can do better than this? Okay, we can improve a lot this solution. Okay, so if we look at here, and for the moment, I won't touch these parameters here. I will go to SV solution. Okay, we have all the variables. So see that we're enabled here transonic correction. Yes. Okay. And now let's do something important. So remember that I always recommend you to do at least one orthogonal correction, even if your mesh is perfect. Okay, I recommend you to do that. And remember that I mentioned that it's very important to do when you have strong physics, very severe physics, just to do more corrections in your outer loop. So see here that let's enable 2 corrections there. We run. And now let's check the solution. So see that now everything has been improved. So here we have a little bit some unboundedness there. See, let me put it, so see here that can be fixed a little bit. It's a little bit oscillatory, but it's a better agreement. See that in comparison to the previous case, see also that we have a very good agreement. And see that now all these problems were solved. See that we have some unboundedness, and we go here, we have some unboundedness as well. But see the importance of doing those additional corrections. So again, my recipe, probably this will be the final one. Also, when you have severe coupled physics like this one, enable at least 2 correctors. Also, you can do something like this, that you can enable the convergence of this outer loop. So then you will define your tolerance, absolute, and relative. Okay, so usually also I play like this. Okay, so sometimes I start at the beginning with 2, and then I let it run, and then I put this one. But also be careful that when you add this one, sometimes it will take many iterations. So you need to monitor the residuals. But in general, doing 2 iterations, it is good. Okay, to alter the corrections. Most of the time, I do 5, and also I pay attention not to do more than 10, because more than 10 starts to become very expensive. So the point, remember that when you do a single iteration, you are redoing everything. So if you do 2 iterations, you are doubling your computing time. If you are doing 3 iterations, you multiply by 3. If you do 10 iterations, you are multiplying by 10 your computing time. So it is a compromise. You need to see if it works or not to have those many iterations. But let me put here 20, and let's run with these tolerances and see what happens. Okay, so it was again very fast. So see what is happening. Okay, let me move here. See that it is iterating, and see that it will monitor these tolerances, and then if it reaches one of these, or this one, or this one, it will stop. So see that iteration 1, 2 here already measures that it arrived to convergence to those to the criterion, and then it will stop in iteration 3. Okay, see that we have that behavior, and at the beginning, usually, as usual, it will take longer. It will take more iteration, but slowly it will start to settle down. And let's go to the beginning. Okay, 1, 2, 3, 1, 2, 3 iterations. Okay, so if you run one of the previous tutorials, for instance, during cavity, you will see that it will do 2 iterations. Okay, the first one, it will measure that already it is converged, and then it will do the second one. So in general, also I like to do 2 iterations. Okay, that will improve a lot your solution. It's true that it will add a large overhead to your computation. So let's keep going out. Let's see what happens at the beginning. So see that 4 iterations. Okay, at the beginning it will do more iterations, and then slowly it might get to 2, or it might get 3, which is okay. So see that here 6 iterations. Okay, so see it starts here 5 iterations. Okay, then it goes. So see that you reach the value here, the tolerance. Probably the most critical one to reach is the pressure. Okay, always is related to the initial residuals, by the way. Okay, so always check your initial residual. Okay, so see that here it goes below the absolute one, this one. And that is what it's doing. So my final advice, enable these corrections. So now we know what to do. Okay, so we go to SV schemes and probably let's address those small fluctuations, oscillations that we have. So let's go and we add a limiter. So I will use the least square, that probably is the most accurate one. So see that you have least square. Point linear is the Gauss method, but it's no based and cell based. Okay, so the point linear is kind of equivalent to least square. Okay, so now that we added that limiter, let's rerun. Plus the outer loops. So see that now it's smaller. Still, we might have something there, but it is smaller, okay, in comparison to what we have previously, and we still have something there. So let's also work it out here. What else we can do to improve the solution? Okay, so let's go and use a more refined limiter. So you have the cell limited qubit, okay? So the difference between this one, when you use these formulations, for the gradients it used by default the min mod. Okay, the min mod is non-differentiable. Now the qubit is differentiable, so it might have some better properties. It might improve the solution. So let's see what happens now. We rerun. And let's monitor the outcome here and see that now it is gone. Very smooth solution. Okay. No more peak there. So this is what we want, a perfect solution. Okay. Okay, so we added this severe one, or not severe, very elaborated one. Again, this kind of limiters, I don't recommend you to put in any problem. Okay, those are very elaborated. You use it when you need it. Okay, like in this case, most of the time going for least square like this is okay, or point linear, or the Gauss linear normal. So let's check point linear to see what happens. So I'm quite sure that we might have something similar to the least square and better than the pure Gauss linear. Yes, you see what we have that. So what we can do now, so we have seen that we add this new limiter, it will solve the problem, but also we can play around with the divergence here. So we are using linear win. We know that this is a severe problem, so let's use this formulation. Let's see what happens if I use this formulation. Linear win V. Okay, V, remember, is specific formulated for vectors, velocity. In this case, it won't make much a difference because it's a 1D measure, but just to show you. And let me go back to the pure Gauss linear here. Let's run. And voila. So we check again and see that we have, again, that small fluctuation there. Well, actually, yeah, we have it there. So let's go and move instead of this one, let's use the min mod. Okay, so let's use V, specific for vectors. We run. See that now it have an influence. See, by using this one, look at that, it's taking many iterations, so it's not converging. So even changing these parameters here will have an effect in your outer loops. Okay, so it was having problems converging. Okay, not necessarily means that your solution will be wrong, but see that after a while it goes to 3. But at the beginning, see that it's taking many iterations. It's not converging. It will reach the total of the maximum and then it will pass. Okay, but see that every single of this iteration is a very approximation of the previous one. So you check the initial residuals, see that are lower. Okay. So as we go here, so you see that they are stalled a little bit. So see the first one, then you iterate, and then start to oscillate. So as we check now our solution, let's see what we have. See that now we don't have that oscillation there. Okay. And you can combine that with the qubit limiter or the Venkata-Krishnan limiter. Okay, those are very, let's say, elaborate limiters. And then you can play with all these methods. We have seen the theory, However, I don't recommend you can play, but as I told you, my favorite ones are Min Mod and Vanlier. Okay, you have other options, so you have also a Super B, for instance, and in this case, the Super B will give you problems. By the way, also monitor your CFL number. So see here that the delta T that we're using is giving us almost in the limit of 1. Okay, so if I go and use the Super B, it diverges. Okay. So the Super B is very sensitive to the delta T. So now if I reduce by half the delta T, meaning also that I'm halving my CFD to 0.5, likely probably it will run. So see, it's running. Okay, let's see how many iterations, 2 iterations as well, and we compare the solution here. See that it is a little bit oscillatory. It's not perfect. It's too compressive. Okay, that is the problem. That this is very compressive. And even if you add the qubit limiter, you will still have that problem. So let's check also the mesh and the solution. So what we have, the domain is this. Okay, it's 1D. We have a lot of cells there. Okay. And then what is happening is that at the beginning, we have high pressure here, low pressure here, then you have here a wall that it will break, and then you will have your shockwave system propagated. You see here. So see here, you see there the oscillations. Okay. So now let's go, for instance, let me go back here, Super B, and let's use the linear method. So we know that the linear, it's very accurate but highly oscillatory. So let's see what happens if we run with linear. Okay. So it seems that we have a good behavior, okay, and actually didn't generate oscillations, okay, that this is strange, okay, or well, not strange, in this case it worked fine. This is a 1D case, you make it a 2D or triangular mesh, there you're going to start to see problems. And as you plot here, see that as in the previous case, you don't have those fluctuations there, very smooth solution. Okay, so let me also eliminate here this limiter. Let me rerun and let's see what happened here without the limiter. Let's see if we managed to get some fluctuations, so a little bit unbounded there. Okay, so now let me go here and change my time discretization. So remember, your CFL is less than 1 Euler is okay, but if you want extra higher accuracy, you can go for a second order. So here, let me use Grant-Nicholson. That also tends to be a little bit oscillatory. Let's see what happened here with the Grant-Nicholson. See that now I start to see more oscillations. Okay, and you have it there. So if we plot the solution, we might see somewhere here, yes, see that you have your oscillation there. So if we want to erase that one, maybe in this case, if we go like this, it will solve that problem. Just want to remind you also that the linear in this case is working because it's one dimensional. Okay, this is a section rather than the rule. See that now this one, while it's erasing that oscillations, is becoming unbounded, which is not okay. So if I go now instead of, oh, that was, well, it was working min mod. Okay, so let me go here now, linear, fully linear here. Okay, now see the behavior there. So the linear is oscillatory. Let me go here and put this one. Okay, whoops. Put it here, run. It was quite fast. Let's see what happened now. This is now see here you have the oscillation. Okay. So this is okay. Previously, I was using the min mod. Okay, So you saw here also the problem with the Krent-Nicholson. Okay, let's go back here and let me put, instead of this one, default here, this one, min mod. Let me use the original one. Run this one. Sampling, done. And let's see what will happen in this setup. So there are some oscillations, okay, it might be acceptable, okay, but it can be better. But usually this is related now to the Krent-Nicholson. So if we go 0 here, which is equivalent to Euler, we're not going to have those oscillations. See that? Not anymore. Very smooth. Okay. Very nice problems. This is very simple, very fast, but you can play with all these numerical schemes. And then also remember that you will have energy, so you can play also with these schemes. So again, the same idea. So I go here, win, highly diffusive. Let's see what happens. So it's putting all this win in all the equations related to the energy equation that we're solving. So we immediately see that it's more diffusive. So again, it's not recommended for energy to go and use win. Okay, it's less diffusive that for velocity, but you see there the diffusion. I really like this method. LUST is like a hybrid between so we'll recall is 75% linear, 25% linear or win. It's a very good it's, well, not very good. I have been playing around with that one, and I'm getting good results. So let me use this one for energy. Okay. And now we're going to see the improvement compared with the win. Okay. It's a little bit sinusoidal, as you see here. Okay. And if I go back now to this one, now let me use this one. So one of the things at the beginning I mentioned that there are many discretization schemes in OpenFOAM available. So generally speaking, don't get lost in that. Remember that you just need to know a win, a linear, a good TBD, and linear win, and probably a bounded linear, like limited linear. That is the only thing that you need. And remember that to use limiters as well. Be careful to not to add a strong, very aggressive limiters. Sometimes if you are interested in computing for forces, do not add a very aggressive limiter here. For instance, you put one here that is very aggressive. So usually like for pressure, put it 0.323. Okay, so remember that this is selective. Default, this is the default method for all gradients, and then you can do it in a selective way. So let's go like this. Let me go like this. And most of the time, this is the setup that I will use. Okay, so Krent-Nicholson 77, it's limited here for pressure, and careful that not to add something too aggressive. Here, I go linear win. Now to go like this, and then after a while I can change it to the vector formulation. And here also I like to use limited linear one. Then remember SV solution. So let's put here, let's say 3,000. Okay, and let's run. Okay, so let's see what is happening if it is converging in the final ones. Previously it was converging. So see that not converge, okay? But I hope it's not a problem. And then we go here. Okay, see that we have some oscillations there. So here, okay, at the beginning, let's go for something more refined. I go for this, and probably also can be related as well to the pressure. In this case, it's also might be critical to have a good limiter for pressure. Okay, I have it here, so let me erase this. Okay, different behavior is still something going on there, and well, likely probably is due to this one. So okay, so also let me show you the influence of delta t just to end this one. So let me reduce half by half. So if I run now, so always reducing the delta t, the time step will improve your solution, but again it will increase your computational time. So there is some improvement there or not. Okay, so easy problem, play with all these options just to get it working. So probably here let's better go back to Euler. In this case the Crank-Nicholson maybe it's not a good choice, so if we go back to Euler, see that things are getting better. Okay, so I think this is all. Feel free to play with all these combinations, but again, just to stress it again, don't get lost here in all the discretization schemes that you will find out. You know that you need sometimes to use a win, then linear, good TVD, and linear win. That's all. And just also understand this concept of the gradient limiter. That's all you need to know. And then for Laplacians, it's according to the mesh quality. Okay, so that's all for this tutorial. Thank you for following on. And well, if you like it, thumbs up. If you didn't like it, just thumbs down. Bye and see you next time.